And here we go, the fundamental theorem of calculus. We're going to start looking at a graph. The graph is shown, and it is y equals f of t. We're given the equation that g of x is equal to the integral from 0 to x of f of t dt. We need to find g of 0, g of 1, g of 2, g of 3, g of 4, and g of 5. So we're going to start with g of 0. So g of 0 is equal to the integral from 0 to 0 of f of t dt. And if we look at the graph, we notice that there is no area under the curve at g of 0. So g of 0 equals 0. The next space is g of 1. G of 1 is equal to the integral from 0 to 1 of f of t dt. So we notice that that's a triangle. From 0 to 1 on the t is a triangle. So the area of a triangle is 1/2 times base times height. 1/2 times 1 times 2 gives me an area of 1. Okay. When we go to look at g of 2, we're working on the integral from 0 to 2 of f of t dt, which is actually equal to the interval from 0 to 1 of f of t dt plus the integral from 1 to 2 of f of t dt. Now, g of 1 was 1, and we notice that when we go to t equals 2, we have 2 more boxes. So we've got 1 plus 2, and that equals 3. G of 3 is actually equal to g of 2 plus the integral from 2 to 3 of f of t dt. We know g of 2 is 3, and when we look at the t values between 2 and 3, it looks like we're adding on about 1.4. So 3 plus 1.4 is 4.4. Now our g of 4 is equal to g of 3 plus the integral from 3 to 4 of f of t dt. And now we know that g of 3 is 4.4. And we're adding that. Well, we notice from 3 to 4 we're now going below the x-axis, so we're adding a negative. And it looks to me like the interval between 3 and 4 has about the same area as the interval between 2 and 3. So I'm going to use a negative 1.4. And 4 plus a negative 1.4 is 3. Now we need g of 5. G of 5, of course, is going to be equal to g of 4 plus the integral from 4 to 5 f of t dt. We know that the area under the curve of g of 4 is 3. And we are adding on, it looks to me like it's probably another negative 1.4. So 3 plus negative 1.4 is 1.6. Now we're actually going to graph our g of x equals the integral from 0 to x of f of t dt. And the way that we do that is we're going to plot our points that we had. Okay, so for our first one, we had g of 0. So when t is 0, f of t would be 0. So we're going to put a point at 0, 0. Our next one was g of 1. When t was 1, then f of t, or g of t, is going to be 1. So there's my second point. I then had another point when t was 2. We would have g of 2 would be 3. So right here is my next point. And I'm going to continue on. So we've got 3, 4.4, 4, 3, and 5, 1.6. We go ahead and kind of draw this curve. Okay, so if we look at the given graph, we can see that g of x is actually increasing from 0 to 3, and we can see that g of x has a max value at x equals 3, But if we look back up at the graph of y equals f of t, that graph was a derivative graph. That's what this dt here represents. If we look back up at this for a second, we see that, oh, the derivative is positive when t equals 0 to t equals 3. Well, that would have to mean that g of x would have been increasing from 0 to 3, and it is. We see that, oh, this derivative changed signs when t equals 3. The derivative changed from positive to negative when t equals 3. And we know that if the derivative changes from positive to negative, we have a max. So therefore, we knew we had a max at x equals 3 even without having drawn the graph. Now we're going to look at the first part of the fundamental theorem of calculus. There are two parts to the fundamental theorem of calculus, and it depends on your textbook whether it's called part 1 or part 2. There is no correct way for designating which one is which. Honestly, it just depends on the textbook. So if the function is continuous on the closed interval a to b, then the function g, which is g of x equals the integral from a to x ft dt, it's continuous on the closed interval a to b, and differentiable on the open interval a b, and equally important, g prime of x, the derivative of g of x, equals f of x. The derivative of the integral is the function. The integral and the dt cancel. Derivative and integration are inverse functions. So right here, the integral sign cancels, the derivative symbol cancels, and we're left with f of t. Or what we're actually going to be left with is f of x. Inverse operations. Let me show you an example. G of x equals the integral from 0 to x, the square root of 1 plus t squared dt. dt means I've already taken a derivative here. This is the derivative. They want us to find g prime of x. We know f of t is continuous. F of t is our square root of 1 plus t squared. We know f of t is continuous. Therefore, g prime of x, the derivative of g, is equal to the square root of 1 plus x squared. We replace the t with the x. We cancel the integration and the derivative symbol. And we would also, because we're taking a derivative, we would take the derivative of the x that we replaced the t with, but the derivative of x is 1, so we're good. Okay. Second example, s of x equals the integral from 0 to x sine of pi t squared over 2 dt. We know that f of t is continuous because sine functions are continuous. So the derivative of s of x, s prime of x, equals the function, so that's sine pi, replace t with x, so that's x squared over 2, and then take the derivative of x because I did replace t with x. Well, that derivative is 1, so I'm good, I continue. Okay, and one more example with the chain rule this time. We're going to find d dx, find the derivative of the integral from 1 to x to the 4th of secant t dt. Secant t is continuous on our function here, so we're good. So our derivative is going to equal secant, replace t with x to the 4th, and the derivative of x to the fourth is 4x cubed. So my derivative of secant t dt of the, my derivative of the integral from 1 to x to the fourth of secant t dt equals secant of x to the fourth times 4x cubed. You might notice that the a value changed to 1, where in the previous two examples it was 0. That's perfectly okay because the derivative of a constant, and it doesn't matter what the constant is always 0.